This is section 2.4, linear inequalities. These are the topics we'll be covering. Let's deal with some terminology and concepts to begin with. An inequality basically results when we take any equation and we replace the equal sign with one of the following notation: less than or equal to, greater than or equal to, less than, or greater than. Now when we looked at solved linear equations, this is very simple because we will follow the same steps that we followed when we solved linear equations. So linear inequalities use the same methods as linear equations do. However, there is one caveat. There's one thing we have to be aware of, that when dealing with inequalities, we must flip the inequality when we multiply or divide by a negative number. So if I have a less than, and I multiply or divide by a negative number, I will have to change by a greater than. And that's when I'm doing that to both sides. Let's see some examples of this. First example is on our left. We have negative 3x minus 4 is greater than 13. We're going to add 4 to both sides. We get negative 3x is greater than 17. Divide both sides by negative 3. I get x on the left-hand side, negative 17 on the right, thirds on the right-hand side. Please notice what happens to the sign. It flips from a greater than to a less than. The reason it does that is because I divided both sides by a negative number. We look at our next problem. We have negative 2 times x minus 4 is less than or equal to 5x plus 7. We're going to distribute on the left-hand side. We get 2x minus 8 is less than or equal to 5x plus 7. I'm going to subtract 2x from both sides. Subtract 7 from both sides. We get negative 15, less than or equal to 3x. Now notice when I divide by 3 this time, my sign does not change. The reason is that I'm dividing by a positive 3. We get negative 15 thirds is less than or equal to x. So negative 5 is less than or equal to x. These are very simple methods, but usually when we do math, we introduce new notation as well. So this is the notation we're going to deal with. We're going to look at what's known as our interval notation. And just like the domain, we need to use intervals to describe our answers with inequalities. If we have an inequality, x is greater than or equal to negative 2. The interval is from 2 to infinity. We use the brackets here because we have the equal part to it. So we have a bracket, means it includes 2, and it goes to infinity, and we use an open parentheses on infinity. If we were to graph this on a number line, we'd start at 2, we'd do a bracket, then we have simply an arrow pointing to the right to represent it goes to infinity. If we have x is less than 3, these are all numbers less than 3, so we have our interval again. The smaller number goes on the left-hand side. So that gives me negative infinity to 3. There's an open parentheses on 3 because it's a less than sign. And again, if I were to graph it, I have an open parentheses and then an arrow pointing to the left showing it goes to negative infinity. If I have an interval from negative 3 less than x less than or equal to 2, this is where my brackets are mixed matched because I have less than here for the first one, so I have an open parentheses with negative 3. I have less than or equal to with the 2, so I have a bracket with the 2. So I have the open parentheses negative 3 comma 2 bracket. This will also be reflected in our graph with an open parentheses on the left and a bracket on the right. And finally, if I have some simple situation where I have 5 to 9 with not equal to on each one, 5 less than x less than 9, we have the interval from 5 to 9 with open parentheses on each. And if we're to graph it, we would simply use open parentheses on each and shade in between. Now we can extend this concept of solving inequalities. Now when we solved equations, we only had 2 sides. We had a left side and a right side. Sometimes when inequalities, you can have 3 sides. You can have a left side, an inside, and a right side. This is an example. We have negative 5 less than or equal to the quantity negative 2 times x minus 4 less than or equal to 14. Now what we're going to do is we're going to follow the same steps we did before, but your rules apply. Whatever you did one side, you did to do the other side. In this case, whatever we did to one side, we have to do to both other sides as well. If we start out with this, negative 5 less than or equal to negative 2 times x minus 4 less than or equal to 14. I have negative 5 less than or equal to, I'm going to distribute in the middle, negative 2x plus 8, which is less than or equal to 14. I'm going to subtract 8 from every side now to get rid of the 8 in the middle. Negative 5 minus 8 is negative 13. I'm left with just the negative 2x in the middle, and 14 minus 8 is 6. I now have negative 13 less than or equal to negative 2 less than or equal to 6. I'm going to divide everything by negative 2. Remember, when I divide by negative, the signs change. So I have 13 halves greater or equal to x greater or equal to negative 3. So my interval notation, the smaller number goes first, negative 3 comma 13 halves. There's brackets on each because they're both equal to, and my graph reflects it as well when I plot my points and mark the endpoints of the interval. Let's look at an example of a word problem. A 100 milligram dose of a medicine is administered and metabolized in the body at a rate of 12 milligrams per hour. I'm going to go ahead and add in constant rate here because we want to assume this is a linear function. The function of this model is t of x equals 100 minus 12x. Determine how long before there is less than 20 milligrams in the body. So I want to find out when the amount of the substance in the body, when the t of x is less than 20. So t of x is 110 minus 12x is less than 20. I'm going to add 110, subtract 110 from both sides to get negative 12x is less than negative 90. Divide both sides by negative 12, my inequality flips, so x is greater than 7.5. So after 7.5 hours, there's less than 20 milligrams left in the body.